for Lesson 14, Computing Actual Lengths from a Scale Drawing. So let's take a look at example 1. The distance around the entire small boat is 28 4/10 units. The larger figure is a scale drawing of the smaller drawing of the boat. State the scale factor as a percent, and then use the scale factor to find the distance around the scale drawing. So let's start with the scale factor. Well, the horizontal distance of the smaller boat is 8 units. The horizontal distance of the larger boat is 22 units. The vertical sail distance of the smaller boat is 6 units, and the vertical sail distance of the larger boat is 16.5 units. So again, remembering that the scale factor is a quantity is equal to percent times the whole, we're going to use the smaller boat as the whole. So the length of the large boat is going to be equal to the percent times the length of the smaller boat. So therefore, 22 is going to be equal to percent times 8. To solve for the percent, it would be 22 divided by 8, or 22 over 8, which is 2 75/100ths, which means it would be 275%. If we check the other lengths, 16.5 is equal to percent times 6. So 16.5 divided by 6 is the percent, which is 2 75/100ths, which is also 275%. So the total distance, knowing that we have our scale factor, is the distance around the small boat is 28 4/10 units. And the distance around the large sailboat would be 28 4/10 times 275%, which would be 28 4/10 times 2 75/100ths, which is 78 1/10. Therefore, the distance around the large sailboat is 78 1/10 units. All right, let's go ahead and discuss this first example. Recall the definition of a scale factor of a scale drawing. The scale factor is a quotient of any length of the scale drawing and the corresponding length of the actual drawing. Since the scale factor is not given, how can the given diagrams be used to determine the scale factor? Well, we use the grid lines on the coordinate plane to determine the lengths of the corresponding sides, and then use these lengths to calculate the scale factor. So that's why we use the sails and we use the length of the boats. So which corresponding parts did you choose to compare when calculating the scale factor, and why did you choose them? Well, the horizontal segments represent the deck of the sailboat are the only segments where all 4 endpoints fall on the grid lines. Therefore, we can compare these lengths using whole numbers. If we knew the measurements of all the corresponding parts in both figures, would it matter which two we compare to calculate the scale factor? Should we always get the same value for the scale factor? Well, yes, there is no indication in the problem that the horizontal scale factor is different than the vertical scale factor, so the entire drawing is the same scale of the original drawing. Since the scale drawing is an enlargement of the original drawing, what percent should the scale factor be? Well, since it's an enlargement, the scale factor should be larger than 100%. How did we use the scale factor to determine the total distance around the scale drawing, or the larger figure? Well, once we knew the scale factor, we found the total distance around the larger sailboat by multiplying the total distance around the smaller sailboat by the scale factor. All right, let's try this with exercise 1. So trying exercise 1, use the information from example 1. Continue the video to check your work and make any corrections. All right, you should be done with exercise 1. So first, you want to determine the scale factor. Since the smaller path is a reduction of the original drawing, the scale factor should be less than 100%. Since the smaller path is a scale drawing of the larger path is the whole in the relationship. So, using quantity is equal to percent times the whole. To determine the scale factor, compare the horizontal segments of the smaller path to the larger path. So that means small path is equal to percent times the large path. Therefore, 2 is equal to the percent times 6. And when we solve for percent, we would get 1/3, and 1/3 as a percent would be 33 1/3%. To determine the length of the smaller path, multiply the length of the larger path by the scale factor. So therefore, 32 4/10 times 1/3 is 10 8/10. So the length of the shorter path is 10 8/10 units. Did we have to use the horizontal segments of the paths? No, we could use the vertical segments of the paths. Since they are proportional, we would get the same scale factor percent. If we convert 1/3 to a decimal, does it change our answer? Well, yes, because 1/3 is a decimal, is repeating, so we would not get an exact answer if we convert the decimal values to fractions. So in this case, we have to leave them as fractions. All right, let's take a look at example 2. Sherry designed her garden as shown in the diagram on your lesson worksheet. The distance between any two consecutive vertical grid lines is 1 foot, and the distance between any two consecutive horizontal grid lines is also 1 foot. Therefore, each grid square has an area of 1 square foot. After designing the garden, Sherry decided to actually build the garden 75% of the size represented in the diagram. What are the outside dimensions shown in the blueprint? Well, the blueprint dimensions, the length is 26 boxes, which means it's 26 feet, and the width is 12 boxes, which would be 12 feet. So part B, what will the overall dimensions in the actual garden? Write an equation to find the dimensions, and how does the problem relate to the scale factor? So the length is, for the actual, is going to be 75% or 75 hundredths times 26, which means it's going to be 19 1/2 feet. The width, the actual, is going to be equal to 75% or 75 hundredths times 12, which would give us 9 feet. So the actual garden dimensions, which is 75% of the blueprint, is 19 1/2 feet by 9 feet. Since the scale factor was given as 75%, each dimension of the actual garden should be 75% of the original corresponding dimension. The actual length of the garden, 19 1/2 feet, is 75% of 26, and the actual width of the garden, 9 feet, is 75% of 12. So if Sherry plans to use a wire fence to divide each section of the garden, how much fence does she need? So here is the dimensions of the blueprint. So the total amount of wire needed for the blueprint is going to be 26 times 4 plus 12 times 2 plus 4 1/2 times 4 plus 14. If you add all those up after multiplying the repetitions there, you get 160. So the amount of wire needed is going to be 160 feet. So now let's talk about the new dimensions of the actual garden. Well, the length, 19 1/2 feet from part B, and the width, 9 feet, also from part B. And now we have to do the inside borders. So 75% or 75 hundredths of 4 1/2, which would be 3 375 thousandths, or 3 375 thousandths feet. So we take 75% of 14, which would be 10 1/2 or 10 1/2 feet, and the dimensions of the inside borders are 3 375 hundredths feet by 10 1/2 feet. So let's take a look at the total wire with the new dimensions. Well, it would be 19 1/2 times 4 plus 9 times 2 plus 3 375 thousandths times 4 plus 10 1/2, which is 120. Or we could have also done 75% of 160, is also 120. So the total wire with the new dimensions is 120 feet. Let's take a look at the simpler way to calculate this. Well, 75% of 160 feet is 120 feet. Well, if the fence costs $3.25 per foot plus 7% sales tax, how much would the fence cost in total? Well, $3.25, which is 3 25/100, times 120, which was the total amount of feet, is 390. Well, 390 times 1 7/100, because again we are charging 7% tax. If the original is 390 and then we want 7% more of that, that's why we multiply by 1 7/100. When we do that, we get 417 30/100. So the total cost, if we write this in money, is $417.30. All right, let's take a look at what we've done so far. So why is the actual garden a reduction of the garden represented in the blueprint? Well, the given scale factor was less than 100%, which results in a reduction. Remember, it was 75%. So does it matter if we find the total fencing needed for the garden in the blueprint and multiply the total by the scale factor versus finding each dimension of the actual garden using the scale factor and then determining the total fencing needed by finding the sum of the dimensions? Why or why not? What mathematical property is being illustrated? Well, no, it doesn't matter. If you determine each measurement of the actual garden first by using the scale factor and then add them together, the result is the same as if you were to find the total first and then multiply it by the scale factor. If you find the corresponding side lengths first, then you are using the distributive property to distribute the scale factor to every measurement, which looks like this. 75% times each one of the dimensions gives us our new dimensions, or we can just do 75% of the total, which gives us 120. Either way you do it, 120 is equal to 120. By the distributive property, the expression 75% times the quantity of 104 plus 24 plus 18 plus 14 and 75% times 160 are equivalent, but each reveals different information. The first expression implies 75% of a collection of lengths, while the second is 75% of the total of the lengths. If we found the total cost including tax for 1 foot of fence and then multiplied that cost by the total amount of feet needed, will we get the same result as if we were to first find the total cost of the fence and then calculate the sales tax on the total? Justify your reasoning with evidence. How does precision play an important role in the problem? Well, it should not matter. However, if we were to calculate the price first, including tax per foot, the answer would be $3.25, which was the price per foot, times 1 7/100, which was the tax, would give us 3 4,775 10,000ths. When we solve a problem involving money, we often round to 2 decimal places. Doing so gives us a price of $3.48 per foot in this case. Then to determine the total cost, we multiply the price per foot by the total amount, giving us 3 4/800 times 120 is $417.60. If the before tax total is calculated, then we would get $417.30, leaving us a difference of 30 cents. Rounding in the problem early on is what caused this discrepancy. Therefore, to obtain the correct precise answer, we should not round in the problem until the very final answer. If we had not rounded the price per foot, then the answers would have agreed. 3 4,775 10,000ths times 120 would give us $417.30. So again, read this answer very carefully and understand what happens when we round too soon, especially when we're dealing with money. So obviously if there's a discrepancy of 30 cents, you wouldn't want to pay 30 cents more than what is actually due. So when you figure things out like this, rounding at the very end is what you need to do instead of rounding at the beginning. So rounding aside, what is an equation that shows that it does not matter which method we use to calculate the total cost? What property justifies this equivalence? Well, 3 and 25/100ths times 1 and 7/100ths times 120 is the same as 120 times 3 and 25/100ths times 1 and 7/100ths. These expressions are equivalent due to the commutative property of multiplication. All right, let's take a look at example 3. Race car number 2 is a scale drawing of race car number 1. Their measurement from the front of car number 1 to the back of car number 1 is 12 feet, while the measurement from the front of car number 2 to the back of car number 2 is 39 feet. If the height of the car number 1 is 4 feet, find the scale factor and write an equation to find the height of car number 2. Explain what each part of the equation represents in the situation. So again, scale factor. The larger race car is the scale drawing of the smaller. Therefore, the smaller race car is the whole in the relationship. Remember that it's important to identify what is the whole and what is going to be the quantity. So using quantity is equal to percent times whole, we know that the larger car is going to be equal to a percent of the smaller car. So therefore 39 is going to be equal to a percent times 12. When we solve for percent, 39 over 12 is 3 and 25/100ths, or 325%. So let's apply that to the height. 3 and 25/100ths times 4 is 13. So therefore the height of car number 2 is 13 feet. The equation shows that the smaller height, 4 feet, multiplied by the scale factor of 3 and 25/100ths, equals the larger height, which is 13 feet. All right, so let's go ahead and discuss what we just did. By comparing the corresponding lengths of race car number 2 to race car number 1, we can conclude that race car number 2 is an enlargement of race car number 1. If race car number 1 were a scale drawing of race car number 2, how and why would the solution change? Well, the final answer would still be the same. The corresponding work would be different. When race car number 2 is a scale drawing of race car number 1, the scale drawing is an enlargement, resulting in a scale factor greater than 100%. Once the scale factor is determined, we find the corresponding height of race car number 2 by multiplying the height of race car number 1 by the scale factor, which is greater than 100%. If race car number 1 were a scale drawing of race car number 2, the scale drawing would be a reduction of the original, and the scale factor would be less than 100%. Once we find the scale factor, we then find the corresponding height of race car number 2 by dividing the height of race car number 1 by the scale factor. All right, so let's go ahead and try this with exercise 2. So using the information from examples 2 and 3, solve the exercise. Check your answers by continuing the video. All right, you should be done with exercise 2. So, comparing your work to the work here, if you have any questions, again, make a note and bring it to class. All right, so now let's try it with exercise 3. Again, take a look at the work we did in examples 2 and 3, and also in the previous exercise. Try it and then check your answers by continuing the video. All right, you should be done with exercise 3. And this is the answer. Check your work with the answer, and if you have any questions, make a note and bring it to class. All right, let's wrap this up. So how do we compute a scale factor when given a figure and a scale drawing of that figure? Well, again, we use the formula quantity is equal to the percent times the whole. We can use corresponding lengths from the original and the scale drawing as the whole and the quantity. The answer will be a percent, which is also a scale factor. How do we use the scale factor to compute the lengths of segments in a scale drawing and the original figure? We can convert the scale factor to a percent and then use the formula quantity is equal to percent times whole. Then we would replace either the quantity or the whole with the given information and solve for the unknown value. All right, we'll see you in class.